Hello, I welcome you all to this channel again. So in this presentation, we shall see solutions to previous appeared CSIR NET questions on magnetic properties of coordination compounds. So if you have not watched my previous video, please watch that previous video where basic aspects regarding the magnetic properties of coordination compounds that has been given to you, right? So there even you can find these questions, and if you look at that video, you should be able to solve these questions by yourself. You can just try those questions, and you can just verify the solutions or your answers with this presentation. Let us begin with the presentation. Question. It is the correct d electronic configuration showing spin orbit coupling. See, spin orbit coupling has been asked here, but what I assume is that, so this question, it should have been orbital contribution. Essentially they are expecting orbital contribution. This fact I have verified it in Huibu, right? So spin orbit coupling, usually it will be observed in the case of lanthanide complexes, but in the case of if we just talk about transition metal complexes, so this T2G EG, this distribution, it shows that they are asking about this itself, orbital contribution itself. So orbital contribution, that can be just checked by checking the electronic configuration of this or these electronic configurations in terms of crystal field theory. Of course they have given that itself. So if we distribute it, so if we write this T2G6 EG2, T2G6 EG0 in this way, see here it is T2G6, it is even distribution. So whenever you have, this T2G6 or T2G orbitals, when they are evenly filled, then you cannot expect any orbital contribution. So here also they are evenly filled, right? Here if you look at in this configuration T2G4 EG0, it is uneven distribution of T2G orbitals. So there or here you can expect orbital contribution, right? So when orbital contribution is there, maybe they have considered when orbital contribution is possible, then spin orbit coupling will also be possible. In that sense, this question they must have framed. And if you look at the fourth option, it is again even distribution of T2G orbitals where orbital contribution is not possible. So answer, it should be this option C. So answer for this question is option C. Right, next question. So it is, for the following complexes, the increasing order of magnetic moment spin only value. Very simple. What we are supposed to do is we should identify this D system. Say it is TiF63 minus, what is the oxidation state of titanium, that we are supposed to find out. Based on that, what D system it is, that we should work out. And then all our octahedral complexes, according to crystal field theory, we can just write their electronic distribution in T2G and EG orbitals. And then number of unpaired electrons we can work out, and based on number of unpaired electrons, easily this question it can be worked out. So that has been done here. If you look at this I hope this you should be able to make out that it is titanium in 3+ oxidation state. So if you do not know this, you just try to learn this fact first, how to find out the oxidation state. Maybe you can take this as X. It is very elementary thing. So you can take the oxidation state of metal atom to be X, and then you can work it out. Right, I assume or I hope you know this fact. So readily I am taking the oxidation states. Titanium, it is in 3+ oxidation state, and when titanium is in 3+ oxidation state, it will be D1, 1 unpaired electron. So here CR it is in 3+ oxidation state. We can just verify this to be D3 system. So D3 system, weak ligand, it is a D3 T2G3, which means 3 unpaired electrons. And next one, this is Mn, it is in +3 state. Mn, when it is in +3 state, it will be D4 system, and D4 system, it will in weak field, it will give this distribution. So therefore 4 unpaired electrons. And then last one, CO3 plus, CO3 plus 3 minus, it is I guess some, yeah, it's correct, CO3 plus F. See this F being very weak ligand, so in this case it should be high spin complex, and therefore 6 electrons they have been distributed this way. And D6 distribution, so it will also leave us with 4 unpaired electrons. So here also we have 1 2 3 4 unpaired electrons. Here also we have 4 unpaired electrons. Here 3 unpaired electrons, and here 1 unpaired electron. Spin only magnetic moment, it will be directly proportional to number of unpaired electrons. So the order it should be, so minimum it should be A, right? So then B with 3 unpaired electrons here, and this MnF63 minus as well as COF63 minus. Both of them, they have got 4 unpaired electrons, so they have got same number of unpaired electrons, and therefore their spin only magnetic moment value, that should also be same. So answer for this question, therefore this A greater than B greater than C and greater than D, so that is correct option, option D. Option D is the answer for this question. Let us go to the next question. Right, so it is the species with highest magnetic moment. Again same thing, whatever we have done for the earlier question, same thing is to be repeated for this also, right? But only tricky thing here is that one of the option B, what they have given is it's an organometallic compound, and in case of organometallic compounds, this is chromosine. So chromosine molecular orbital distribution, if you know, then only you can predict the correct number of unpaired electrons in this. Otherwise this question, it would become difficult. But this option A, option C and option D, if you look at, there will not be any problem. You can straight away find out the number of unpaired electrons. Right, let us see how this question it can be solved. So this one, it should be easy. It will be D3 system, 3 unpaired electrons. Then nickel, let us go to this second option first. So this in this case directly I have given that number of unpaired electrons, in this case it will be 2, right? So how the number of unpaired electrons in this case it will be 2, that we shall see when we go to molecular orbital picture of this kind of complexes. So I directly assume the number of unpaired electrons, or from literature I have taken it to be 2, right? So whereas for option C and option D, in conventional method you can work it out. Cobalt is in 3+ oxidation state, so cobalt only with F it will form a weak field complex, right? Otherwise cobalt in 3+ oxidation state, usually with all other ligands, usually it can form strong field complexes itself. So though it is a D6, we have this distributed T2G6 distribution, and therefore here we can expect 0 unpaired electrons. And nickel EDTA complex, it will be D8 system with 2 unpaired electrons. Nickel octahedral complex, always they will have 2 unpaired electrons. So now here it is 0, right? So since here it is 0, definitely this cannot be the option. CO, this cannot be the option, right? And if you compare this option A and option D, so definitely what you can find is option D you can eliminate, because it has just 2 unpaired electrons. So now even if you do not know about option A and option B, you will be able to mark either A or B. Answer either it should be A or B. Further, to distinguish or to find out the correct answer between A and B, we should know that. So this option A, it has 3 unpaired electrons as I have described, whereas this has 2 unpaired electrons. So therefore spin only magnetic moment, it will be definitely more for option A. So option A is the answer for this question. Okay, next one. So what they have done here is they have asked for this complex CrCl63 minus complex. They have asked both spin only mu s as well as mu L plus s or s plus L. So both the magnetic moments they have asked. So how it can be calculated? First thing same, we should just find out the number of unpaired electrons, and number of unpaired electrons, it will come to 3. So Cr, it is in 3+ oxidation state. So Cr, it is in 3+ oxidation state. Cl, we do not, it's not necessary to bother whether it is a strong field or weak field, because D3, whether it is strong or weak, it doesn't matter. Number of unpaired electrons, it will be 3 itself. So for 3 unpaired electrons, spin only magnetic moment, easily you can calculate. Say 3.87 Bohr magneton, it will come to. N value substitute it to be 3, and 3 into, this is 3 plus 2, 5 into 3 is so it is 15, so it's close to root 16 or slightly less than 16, so therefore it should be 3.87 Bohr magneton, right? So just even if you do this thing, you can look at these two options, A and C, which have got 3.87 value for spin only magnetic moment, and here it is different. So therefore readily you can eliminate option B, and option B and option D can be eliminated even if you just calculate spin only magnetic moment. Fine. Further, to calculate this mu L plus S, right? So we may have to use this formula, and this formula it has been given. But one thing what you can notice here is it is T2G3. So it is even distribution of T2G orbitals. So exactly speaking, here orbital contribution, it will be negligibly small. But somehow in the question it has been asked, and therefore just we can go with this formula and we can try to work out that. Fine. Now the formula for spin plus orbital, when both the contributions are there, the corresponding formula it has been given to you, it is this. So it is square root of 4s into s plus 1 plus l into l plus 1, right? So now we should know the value of capital S and capital L. So capital L and capital S value, if you have done or if you have watched videos on term symbol, then you will be knowing how to work out this. See, those who have not watched my videos on term symbol, so you can just first watch them to understand how to calculate this L and S values. So here, see, if you distribute the electrons in this way, L value it will be plus 2 plus 1 0, it will come to 3, and total spin value for 3 unpaired electrons, it will be 3 by 2. So next thing, it is very simple, just substitute these L and S values here. Simplify the things, right? What you get is root 27 you get. So root 25 is 5. So root 27, it should be slightly greater than that. So your answer, it should be 5 plus something. So this plus, it simply represents the answer, correct answer. It is 5 point something or 5 plus something, Bohr magneton. So now if you look at corresponding options, so here option A you can find that, whereas option B it is 6.34, which is not possible. So if this would have been 36 plus more than 36, then we could have thought of this, but if you do the correct calculations, root 27, it can be 5.20. So therefore, the correct answer for this question, it cannot be option C, and it should be option A. Right. Let us go to the next question. Yeah. Next one, the room temperature magnetic moment for a monomeric copper 2 complex is greater than 1.73. This may be explained using the expression. Directly expression they are asking and nothing else they are expecting from you. If you know the fact that copper in its 2 plus oxidation state, it will have one unpaired electron, and its corresponding ground state, it will be E, right? So from Orgel diagrams, this can be easily predicted. In fact, it will be EG for octahedral complex, right? Here we can assume that copper, it has formed octahedral complex, and even if copper it is forming tetrahedral complex, number of unpaired electron, it will be 1 itself, right? Now what we can do is, what they say is, this value, it is slightly greater than 1.73. so for one unpaired electron, spin only value, it is 1.73, square root of n into n plus 2. If you apply that formula, spin only value what you get is 1.73. but what they say is, the value, exact value, mu effective, it is slightly greater than this. And if you know the fact that for the slight variations, we can readily go with this formula. If you know the fact, readily you can answer, you can mark this to be the answer, right? Further, even this is a typical example. Even if you do not know that A is the correct option, you can just think of eliminating B, D, and C, and based on that also, it should be possible for you to work out the answer to be A. See, now what they say is, mu effective, if it was square root of n into n plus 2, then the value, it would have been exactly 1.73. Option B I am talking about, right? But they say that it is greater than 1.73, so this may not be the appropriate formula. So if you look at option D, so in option D, mu effective, they have given that square root of j into j plus 1. In fact, we do not have any formula of this kind. So we have one formula considering spin orbit coupling, spin coupling, and orbital coupling. We have one formula which states that it will be mu effective is equal to g into square root of j into j plus 1. But in this particular option D, see, this the g is missing, so therefore definitely this cannot be the answer. You can eliminate this also, right? And now if you look at this, ground state, it is E here. So in this case, ground state, it is E. Or even if you simply look at T2G distribution, it is even distribution. In this case, orbital contribution, it will be negligible or it will be quenched. So therefore, we need not even go with this formula, right? Or what you can do is, the other option is, you can just calculate capital S value and capital L value, and you can put the values in this equation, and you can just calculate mu effective. That will be far greater than 1.73. On that basis, even you can eliminate option C, right? So if you eliminate these three options, then also you are left with only this. So answer A should be option A should be the answer for this. If you readily know this formula, option A, if you readily know that, then it is fine. Otherwise also, this B, C, D, if you carefully eliminate, you are left with option A, and that will be the correct answer for this, right? Next, the complex that shows orbital contribution to the magnetic moment. Again, this is same thing. You can just understand the importance of this orbital contribution, right? So the only point, definitely there are other methods sometimes even if this is the ground state, then orbital contribution will be there, or if this is the ground state, orbital contribution will not be there. In that way also this orbital contribution it will be explained. But what I consider is easiest way is to just remember unevenly distributed T2G orbitals, they will have contribution, orbital contribution, they will definitely have orbital contribution, right? So if T2G orbitals they are evenly filled, then you can just think that your orbital contribution it will not be there. This I consider to be the easiest way to remember, right? So to summarize things, one point which should be kept in your mind, you can just keep this aspect in mind. Unevenly distributed EG orbitals, it will lead to Jahn-Teller distortion. Unevenly distributed EG orbitals, right? So Jahn-Teller distortion, for that also I have made a dedicated video, you can just watch that if you are interested. Unevenly distributed EG orbitals, they will be mainly responsible, I'm carefully using the term mainly, mainly it will be responsible for Jahn-Teller distortion, whereas unevenly distributed T2G orbitals, that will be responsible for orbital contribution. Just you can mention, or just you can remember this fact. Based on this fact, both the things, Jahn-Teller distortion when it is expected and orbital contribution when it is expected, both the things it can be worked out. Fine, let us come back to this question again. So if you come back to this question again, it is the same method. So I will not again go with in detail. See here, it has been worked out. This is D9 system, electrons have been distributed, D8, D7, D3, how it comes to this. By this time, it should be possible for you to work it out and distribute the electrons in T2G and EG orbitals, right? So here it is evenly distributed T2G orbitals, here no, and here it is evenly distributed, here it is again evenly distributed. So therefore only in this option C, CO, H2O6 times, here it is uneven distribution of T2G orbitals, and option C should be the answer for this question. Fine, next question. This is interesting question, right? So last but one question, we had got the formula, and the same formula, the values are to be substituted here, and problem is to be worked out. So in fact, I assume this to be a little difficult question, because mathematical calculations, they are not very simple here. So cancellation, simple cancellations, they are not occurring. I really do not know why they have asked this question, but this can be definitely solved in this way, right? We have the formula mu effective is equal to mu s into 1 minus alpha lambda divided by delta. So while explaining, so I had made a slight mistake, that probably I said this lambda, it should be expressed in terms of centimeter, but no, even is this, it should be expressed in terms of centimeter inverse itself, right? So even while writing, I remember I had just written it is to be centimeters, but no, it should have been centimeter inverse. Fine, very important thing, this should be in centimeter inverse, even this should also be in centimeter inverse. So the value of alpha, it depends on the ground state, and for copper complex in the earlier problem itself, we have seen that alpha, it depends on ground state is E, and therefore it is 2, right? And mu s for this one unpaired electron, it will come to 1.73. So the slight deviation, it will be given by this fact, and that is worked out by 1 minus alpha value 2. Very important thing, lambda value, it is minus 625, that we are supposed to substitute. In fact, even I had missed it in the beginning, and I got wrong answer, but here it is minus, sign is important for this lambda value, that should be substituted. And this is directly given in terms of centimeter inverse itself given, so straight away I'm substituting it to be minus 625. You please neglect this part. Fine, then delta value for copper complex, only one band it will be possible, and that should itself correspond to delta value. It is given to be 625 nanometer, but important thing, this is to be converted to centimeter inverse, for which this is in lambda. So lambda reciprocal is to be taken, therefore this again in nanometer, that has been converted to centimeter, and 1 over this value in centimeter, that will give me delta naught in centimeter inverse. For that purpose, it has been divided, this value 1 over this value has been taken, right? So this mathematical simplification, if you go, this will turn out to be minus of minus, it will become plus, and this whole value, it turns out to be 0.078, right? So then further, this 1.73 into 1.078, it will come to 1.86 mu b, and the correct answer 1.86, I think they have not given. So the nearest what we can find out is, or maybe if we further exact calculations if we do, definitely we may get the correct answer to be 1.81, and Now the best choice, it is this option B. So for this question answer, it should be this option B, right? So these were the questions related to magnetic properties. There are some other aspects associated with magnetic properties. One important fact is it's about spin crossover. So I'll just looking at the questions. If it is necessary, I am thinking to make a video on just a very small video on spin crossover systems too, and there I shall take up the remaining questions, some questions remaining which have remained in connection with this magnetic properties. There I'll try to take up those questions, and even one question, once a question has been asked related to time dependent time or temperature dependent paramagnetism, that aspect also I'll try to cover that itself, right? Otherwise this section, it completely covers magnetic properties too. Okay, thank you for watching this video. Thank you.